Okay, so we are looking at this idea of logic programming. And if you look at a statement of the kind beta is true if alpha 1 comma alpha 2 comma alpha n is true, which is equivalent to saying that beta is true if alpha 1 and alpha 2 and alpha n is true, but we will use the notation comma to stand for and, as is done in the language prologue. Then one can think of uh, the head. So, this is the head and so this is the head and this is the body. One can think of this body as a procedure body. And we can think of the head as a procedure call. If you are familiar with imperative programming, and one can think of unification as passing parameters. So, when by asking whether beta is true, we are in some sense calling a procedure which in turn asks whether alpha 1 is true and alpha 2 is true and alpha 3 is true and so on and so forth essentially. And while doing so, it has to pass parameters which is done by the process of unification essentially. So, we are not looking at bigger formulas, we have so far looked at smaller formulas, and in the last class we looked at this definition of append, which was essentially. So, let me just use A here, nil x 1 x 1, and the other one said that A cons A x and we discussed that how you can make a procedure call with a goal where you have. So, you can ask various questions here. You can ask where all the 3 arguments are specified, or you can ask with any 2 specified and the third one unspecified, and that is what we did in the last class. We tried to show that this goal append cons let me use a notation here, cons this cons is nil comma with cons or that a goal of this kind is true if this variable, actually we call it R, right, for result is bound to cons this forms is forms the and we saw that this binding for this variable r can be obtained through a process of backward chaining essentially. What is the process of backward chaining? That to show, so you match the goal so actually I should use the term unify with either a fact or with the head of a rule. So, if it matches a fact, then you are done, it is true. If it matches the head of a rule, then move to body. In our case, of course, the body has only one formula. So, life is simple for us. Maybe we will also pay some attention to say that what if the body has more than one formula, what does our problem become like essentially. Now, just to sort of emphasize upon this, let us look at another logic program and remember that we had this notion of natural numbers. We had defined this at some point. We had said that the set of natural numbers is a set of 0 followed by successor of 0 which is 1 followed by successor of 0 which is 2 and so on essentially. We had defined the set of natural numbers in this. So, just as we defined the notion of append in a logical sense, let us also define an arithmetic operation which is the operation of plus essentially in a logical sense. So, we will write it again in this same format essentially. So, define addition. We want to be able to say what do you mean by addition logically. So, when you say 2 plus 3 equal to 5, what is the meaning? How do you arrive at that essentially? How do you say that essentially? Now, again just very analogous to the definition of append. So, I am writing it on the same page here. We have a definition for addition and let us call this predicate plus, and the schema of plus is let us say number 1, number 2 and sum. So, if the 3 inputs are numbers which satisfy our notion of what it means to add, then that formula is true essentially. So, remember that whenever we are talking about logic, we are talking about predicates and we are talking about when are formulas true. So, we are saying a formula like plus 2, 3, 5 is true, a formula like plus 3, 7, 10 is true, but a formula like plus 3, 4, 9 is not true essentially. So, we are trying to separate the true formulas from the false formulas and we are trying to find out which all formulas are true, and in the process we will define this notion of addition essentially. So, how can we define addition? The base clause will be that if you add 0 to any number n, you get the number n essentially, and the recursive clause would be that if you add the successor of any number to another number, let us call it m, and you get the successor of the result r, if this was true to start with, if n plus m give you r essentially. So, if you read it in the our original logical notation, then you should read it from right to left. Then you are saying essentially that for all n, for all m, for all r, if plus n m r is true, then plus successor of n with m will give you successor of r is also true essentially. So, this is a program for adding two numbers. So, let us see how this works. Let us call it n 1. Just to use different variable names, we had emphasized upon this point, right. So, if I give a goal as is this formula true, let us say not a very large number, 2 plus 1 and give 3, then of course, you will just plug it in. Remember that 2 is successor of 0, 1 is successor of 0, and you want to show that this formula is true essentially. Sorry, so let me finish that first, plus n m r essentially. So, really the goal should match the left hand side essentially. Now, you can imagine that if my goal was this, plus 3, 4 or I should really get 7 here essentially, if I will not go through the process, but you can see that you can even give a goal as follows. Is this formula true, plus, so successor of 0 with, let us say success, let us work with small numbers here, sorry I want to give this. So, when I say goal, I am basically asking, remember it is an existential query, that does there exist an R such this formula is true essentially. So, obviously, in our human notation we are asking that is plus 2 with some variable give me 3. So, there exists an R plus 2 R 3. Is it true that this formula is true? And then of course, if you can find out that it is 1, then you will find that it is true. Now, we can just repeat this process that we did in the last class very quickly. You will match the first of the 3 arguments with the first of the 3 arguments here, and this match will be done by n let us call it let us give it a new name. So, let us put in a new variable n 2 and also say that okay, we do not need to do that here. R of course remains there. So, I am mixing up things, right. So, I should have called this M. Now, R would be successor of 0, because this R should match the remaining part of this, which is this here. So, I get a sub goal plus successor of 0 M successor of 0. So, again I can now match. I say now n is equal to 0, and I can reuse the same variable names here, it does not really matter. S is equal to successor of 0. So, from that I got this sub goal, from this I get another sub goal, which is plus 0 M successor of 0. Now, this one matches plus 0 n 1 n 1, and what is the substitution, that M is equal to n 1 is equal to successor of 0. So, as a result of this, we can answer yes, and we can say that plus 2, I just write the our notation. Now, M is matched to 1, remember 1 3, or we can say that M is equal to 1. So, what have I done? I have essentially subtracted 2 from 3. So, essentially what I have done is 3 minus 2 is equal to 1. This whole process I have done in this by saying that this is the variable that I am looking for. The second of the two variables is my query and not the third. If I had used the third one, then I would have been adding. If I use the first or the second one, then I am doing subtraction. So, you can see that logic programming, or at least pure logic programming, allows you to be very flexible. As long as you can define what do you mean by addition, you can use that definition in many different ways essentially. You can even give a query like plus are there two numbers n and m which add up to 15 essentially, and you will see that you can try running the program on this, because these are very large numbers. Maybe you can choose 3 or 4 instead of 15, and you can see that yes, you will at least get one answer, and then if you have worked with Prolog, you will know that you can work with more than one answer essentially. You can ask it to give the next answer and so on. So, initially of course, you can see that it will immediately match the first clause and say okay, n is 0 and m is 15, and therefore, 0 plus 15 is 15. So, that the formula is true. Then if you say okay, no, give me another answer, then it will go to the second clause and say that 1 plus 14 is 15, then the third answer is 2 plus 13 is equal to 15. You can generate all the answers essentially. So, there is a lot of flexibility in logic programming. What if we have more than one? We have so far the examples that we have seen have no choices to be made essentially. What if we have choices, and what if we have larger antecedents essentially. So, let us take a small example. to see what is the kind of thing we are talking about. So, supposing and the thing that I am trying to work towards is called goal trees. We will see that essentially this kind of theorem proving is traversing a space which is called a goal tree essentially. So, let us work with an example to make it life simple. Let us say that we have two rules, let us call one rule R 1, we are just this is just for our benefit. We are defining, let us say what it means to be happy, let us say. So, we say that h of x if let us say s of x e of x, we will give mean interpretation to this in a moment I think, but let us say we have two different rules, h of x equal to a of x and p of x. It does not really matter what these predicates mean, but just to make it more accessible to us. So, let us say H stands for happy and let us say S stands for slept well, and let us say this stands for eaten well, let us say this stands for finished assignment, and let us say P stands for played in the evening or something, does not really matter essentially. So, if we are given these two rules which are somebody's definition of being happy, and let us say we are given a lot of facts as well, and the facts are, let me put it in a form of a table. Let us say we are talking about some people, let us say John, Mary, Peter, Jack, and let us say we have some sort of a relational table essentially. So, this is for S, this is for E, this is for A, this is for P essentially, and let us say John has slept well and he has finished his assignment. So, we have Y for that or true for that if you want to say. Mary has also slept well and she is finished playing. Let us say Peter has not slept well, but he has eaten well and he has finished his assignment, and he is also finished playing essentially, and Jack has slept well and eaten well essentially. So, let us say this is some data of some people we have, and then we ask a question, is there somebody who is happy essentially, and we have given this definition of being happy, which says that if you have slept well and if you have eaten well, then you must be happy, and the other one says that if you have finished your assignment and if you have finished playing, then you must be happy, and we have this information about these 4 people and we want to ask essentially. So, if you look at the table, you will see that there are indeed two cases which fit the notion of happiness. One is Peter is happy because he has finished these 2, and Jack is also happy because he has finished these 2, and because of these 2 rules that we have essentially. But how does backward chaining fit in here essentially? So, the space that you want to explore, remember that we want to move from head to body essentially. Now, we have 2 choices here, that we could use the first rule which is sleeping and eating, or the second rule which is finishing an assignment and playing essentially. Now, as we will see as we go along, the prologue would have first tried the first rule and second then tried the second rule, but let us try to visualize the space of the choices that we have essentially, and that space can be seen as a goal tree essentially. So, the goal tree is as follows, that at the top level at the root you have the goal that you want to show to be true, which is happy x. There does there exist somebody who is happy? Now, there are, and remember we are doing the process of backward chaining. So, you can either go to the body of the first rule or to the body of the second rule, and let us say we stick to the lexical ordering which we have the first rule on the left and the second rule on the right, and then we can really understand what prologue does. So, this is R 1 and this is R 2. So, we can either apply R 1 or we can apply R 2 essentially. So, we come to a node here which we can give some name, it does not matter, or we can call it R 1 and R 2. And then when we progress to the body of R 1, we have two things to show. One is that so we have broken down that goal of happy x to the goal of eating well and sleeping well essentially. That is what rule R 1 says essentially. The second rule in a similar fashion says that if you have done assignment and if you have finished playing, then you could be happy essentially. But now there is a difference in the three internal nodes that we have. The top level internal node is a choice, and the choice is you can use R 1 or you can use R 2 essentially. But at the second level with these unnamed nodes that we have, internal nodes, that is not a choice point, that is a node for which you have to visit both the children essentially, and such nodes are called AND nodes, and typically we put an arc across them to depict that they are AND nodes. So, such a tree is called an AND OR tree, and we have studied it. If you have done the AI course, you have studied AND OR trees, but essentially what happens in backward chaining is that the space that you generate is that of an AND OR tree essentially. And then the data that we have, we can just plug it in here. So, John is here. So, when I say write John here, essentially I mean S John essentially, that John has slept well, that the formula S John is true essentially, and S Mary is true, and S Jack is true. For the others I will just write the names. So, Peter is true and Jack is true. For assignment, John is true and Peter is true, and for playing, Mary is true and Peter is true. The solution of such a goal tree is a subtree where leaves are true and what is a subtree? Must take all children at AND node. You must take all children at AND node and one child at OR node. Such a subtree is a solution tree. The leaves must be labeled with true formulas, and at every AND node you must have taken all the children, and at every OR node you must have taken one of the children. So, you can see that there are two solutions here. One is shown in this red here, that there is a subtree which is satisfying this definition, which is obtained by applying rule R1, then going down both the paths, and then again that is an OR node here. All these are OR nodes, because we have not put an arc across them essentially. So, we have taken the path which leads to Jack, and that we have got this OR node. And you can see that there is another solution, which let me draw with blue here, which goes along the other path. So, you must go down both the paths, and here you must go down Peter, and here you must go down Peter. So, one solution contains Peter here, that Peter has done the assignment and Peter has slept well. The other solution contains Jack here, that Jack has slept well and Jack has eaten well essentially. The task of the inference engine is to find one or more of these solutions essentially. The question that we have to ask is, in what order shall we search this tree? And we will take this up in the next class, and we will see that essentially Prolog searches the tree in a depth first fashion, which means it searches the left side first and then moves towards the right side essentially. While you are doing this, you have to be careful that, for example, if you are trying to satisfy slept well and ate well or has eaten well, the value of x must be the same. In this case, if you can find that Jack has slept well and Jack has eaten well, then you have a solution. That condition is there, and that is a constraint imposed by the AND node essentially. And we will see that Prolog essentially does depth first search on this tree, which amounts to saying that it processes your formulas from top to down and left to right essentially. So, it will look at slept first and eaten afterwards, because it slept is on the left hand side and eaten is on the right hand side, and that strategy top to down, left to right, is the strategy which Prolog uses. And you can compare this with what the RetinNet and OPSFI like languages did. There were some problem solving strategy like specificity or recency that we talked about, which decided which one to consider first. Now, this is doing in totally static lexical order, and as we will see, this puts the onus onto the person who is writing the formulas in writing them in a proper order, so that the program works well essentially. So, we have already started talking about it as a program, and the person who is writing these formulas is the programmer essentially, and that leads us to this idea of logic programming.